Hello. Today we're going to be looking at an example of an extended response question. This is taken from the VCE Math Methods 2019 Exam 2. This is question 2 of the extended response question. Because it's from Exam 2, you are allowed to use your CAS calculator and your bound reference to do this. In this question, we're told that an amusement park is planning on building a zip line above a hill on its property. The hill is modeled by this function here. X is allowed to go between 0 and 30 inclusive, and x is a horizontal distance from the origin, y is the vertical distance from the origin. So the first thing we're asked to do is find dy on dx. Before I start actually doing this question, the first thing that I look at is the marks. This question is worth 1 mark. It tells me that it's no marks allocated for working, no marks allocated for anything except for the answer. So all we need to do here is give them the answer. If all we need is the answer, then we should be looking and focusing on using the calculator to try and make our stuff more efficient. One thing that's also worth noting, this is a long question. We've got A, B, C, D, and E is split into 3 separate parts. So because it's so long, we're probably going to end up using these functions again and again and again. So I'm going to start off by using my CAS calculator to define my function. So I'll type define, or I can use the command, and I'm going to say define hill, which is a function of x, is equal to, and then I'll type in my equation. So 3 times x times bracket x take away 30, all squared, divided by, and make sure that we've got this as a fraction so that it divides everything, divided by 2000. One key point with this, and I'll just hit enter, it does it for me. You need to have this times in between the x and the brackets. If you don't have that, the CAS calculator will not know what to do. Anytime you're defining a function, put the multiplication symbol in there. It will make your life so much easier. So to find my function, if we go back to the question, part A is actually asking me to find dy on dx. So I need to find the gradient of this function. If I want to do that, then I just need to hit menu, then calculus, number 4, then derivative. And this will give me the function. So I'll type, I want the derivative with respect to x. So I'll put an x down here, and I'll type hill of x. And there we go. It gives me the equation. This is 1 mark. It's right there, written for me. All I need to do is write it in. So 9, 30 minus x, x minus 30. And then brackets, x minus 10, all divided by 2000. And that's it, 1 mark. Nothing more is needed. So the next part of this problem, it seems really simple. State the set of values for which the gradient of the hill is strictly decreasing. But 97% of students undertaking this exam, 97% of students got this wrong. And why? It should be really easy. You just look at it and you see where it's decreasing. And that looks like it's from 10 down to 30. But that's not what this question is asking. This question is asking us for which the gradient of the hill is strictly decreasing. So not where the hill is decreasing, but where the gradient of the hill is strictly decreasing. And so there's a couple of ways that we can do this to figure out where the gradient is strictly decreasing. We could take the gradient function and take the derivative of that and then look at where that is negative. I'm going to make my life a little bit simpler. So I'm going to go back to my my functions, and I'm going to say define gradient is of x is equal to, and then I'm just going to say I'm going to define my gradient function here, and that's done for me. So now I can go to in the same document. So remember, if we want to make a new page, then we press Control and I, and I'm going to add a graph, and I'm going to call my graph gradient of x. Now, if I look at it and I zoom out to an appropriate region, so I want it between x is 0 and 30 because that's the domain that we're told to consider in this problem. And we go up pretty high with this. let's say 500 and see if that works. That's maybe a bit too high. We'll take it down to 50. We'll take it down even more. Take it down to, I don't know, 10. And so we can see there's clearly a point where we start off positive and then we end up negative. We want where this turns around for strictly decreasing. So we want to find where the minimum of this is. So I'm going to change my view just to make it a little bit more user-friendly. And it looks like we go between 2 and -2 or so. So you can see we've got a real clear minimum here. And we want to know where this turns around. So to find where the gradient is strictly decreasing, we're looking for where this function, this graph of the gradient that I made here, where it's going down. And so that happens at about, well, we need to find the minimum. So we can go analyze graph, minimum, and then we need to select a region. And then, what are you doing? So we go in, we analyze graph, we select minimum to find, then we look at over our region where we can see the minimum clearly is, and it goes till 20. So we are decreasing from the point 0 all the way across to the point 20. And so we're looking for x is between 0 and 20. One key thing with this, so we write our x subset of 0 and 20. So at 20, if we go back to our gradient function, we were at 0. So that's fine. We had a gradient of, our curve flattened out. This was included in the strictly decreasing. However, this 0 is not included in the strictly decreasing because the function stops being continuous at the point 0. So this isn't included. 20 is included because the function keeps going afterwards, but the 0 is not included. I personally think that this question is kind of testament to how careful you need to be when you're doing these problems, because 97% of the state should not be getting this wrong. You need to be really careful when you're answering questions to make sure that you're answering the question that you're actually being asked. Okay. So let's take a look at the next question, part C. So in this, we've got a bit of preamble. We've got a cable for a zip line, and it's being connected to a point at the origin at a height of 10 meters, so at y equals 10, and it's straight between 0 and A. And A is some point that's between 10 and 20. We don't know exactly where. And at this point, this straight section joins the curved section between little a and 30, and at which point it goes down after that. And at those points, it's 3 meters vertically above the hill. So in question C, we're asked to state the rule in terms of x for the height of the cable above the horizontal axis from A to 30. So this last bit here, from A to 30, this is really important because that makes our lives a whole lot easier for this question. If we think about the height of the cable, it's made up of 2 bits. It's the height of the hill, and then it's the height of the cable on top. And we know that at all points, it tells us the cable is then 3 meters vertically above the hill. So if we can get how high the hill is, and then we add 3 meters onto that, that will give us the total height. But we started off with an expression for the height of the hill, this thing here. So all we need to do to answer this is just say the rule for the hill plus 3. So we can say y, or we're asking for the height here, so we might say h is, no, we would say y, sorry, because we have our y-axis here. So for the height of the cable, we have y equals 3, so the 3 meters between the cable and the hill, plus our original expression, 3x x minus 30 all squared over 2000. That's it. We're actually going to skip question D for now, mainly because this uses stuff from integral calculus that we have not covered yet. So moving on to part E. Part E asks us to state the gradient of the cable at A in terms of A. But we already know, so to do this, again, 1 mark means we just need an answer here. We don't need anything else. And so what we can do is we can go back to our gradient function that we had back here, and we can say, okay, if we're at the point capital A, then x equals little a. So let's take this dy dx function that we created way back at the start, and we'll just substitute a into it. And that will be our gradient at the point x equals a. So if we do this down here, we'll get 9 all over 2000, 30, whoops, right, a take away 30 times a take away 10. That's it, another mark. Okay, so the next part of the question asks us to find the coordinates of the point A with each value correct to 2 decimal places. So if we think back, the point capital A occurs when the straight section matches the curved section of the cable, or more specifically, the gradients of these two match. So that means that we need to find where the gradient of the curve matches the gradient of the straight part. So luckily for us, we already have the gradient of the curved part, and that's what we found in part EI. So we can say that 9 times A minus 30, A minus 30 times A minus 10 over 2000 is going to be equal to whatever the gradient of the straight part is. But we don't have a nice handy expression for the gradient of the straight part. What we do have though is we have a diagram, and we know that the straight part goes from this point here, 0, 10, over to this point here, A, B. So we can use rise over run between these 2 points. Now obviously we can't use A comma B like this, but we can use A and then hill of A plus 3, our answer that we got for part C. So we can set up our equation. We had A was, so we use rise over run for this. So our rise, we started at 10, and then we went down to our value of the hill of the cable at the point A. The value of the cable at point A was 3 times A times, I'll just double check my equation, make sure I'm doing this right, A minus 30 squared. Sorry, I had to re-record this part. I found an error, so I'm missing all of my prior solutions. A minus 30 all squared divided by 2000. And then we need to make sure we've got this plus 3 on the end. This plus 3 tells us that we've got the height of the cable, not the height of the hill. And forgetting this plus 3 was the most common mistake that people did when they knew how to do the question, but they still got a wrong answer. And this is what I did, and why I'm re-recording this, is forgetting this plus 3. This just comes down to not understanding the question properly and not understanding what you're being asked properly. So I've got my rise on the top, then I just need my run on the bottom. So on my run, I started at 0 and I went across to the point x equals a. So now I can just set this up in my CAS calculator and I can solve it. I did this already. You just use the solve functionality on the CAS. And so when you do this, actually let's do it. So we'll type solve, and we're looking for our gradient function. So we're looking for gradient of A, when gradient of A is equal to, and then we want a fraction, 10 minus hill, we'll put this in brackets, hill of A plus 3. So that's our rise there. And then our run, we go from 0 to A. So it'll be 0 minus A. And then we're solving this for A. And if we do this, we get 3 solutions, which is not really what we want. We can see from the diagram that we were given that there should only be one solution. But if we take a look at this first value, a equals negative 7.85. Well, we don't want a negative x value here. We were told at the very start of the question that this is only defined from x is 0 all the way to x is 30. So this one is obviously not going to work. That still leaves us with 2 solutions. But if we look, one is 11.15 and one is 26.7. But if we look back at our definition for the point A, back up here in part C, it tells us the height of the cable above the horizontal axis for x, if we look at it in the introduction here, we're told that 10 is less than or equal to A, which is less than or equal to 20. So A has to be between 10 and 20. Our solution that we have here, if I can just find where my calculator is, 26.7, that doesn't work. We can't have 26.73. So we're only allowed to use this middle value based on the stipulations for this question. So we'll go back. We got 11.1157. So our answer, rounded correct to 2 decimal places, we can say that A is equal to 11.12. We've got to get that rounding correct. VCAR will slam you if you don't round your numbers correctly. And so then we'll say that we need to find the coordinates of capital A. And so that's going to be 11.12. But we still need a y value for this. We still need a y coordinate. So we're going to go back to our calculator, and we're just looking for hill of 11.1157. So that's the value of the hill at the point A. To get to the cable, we need to add 3 on top. This gives us a value for the cable of 8.946, which when we round that will give us 8.95. Notice when I did this, I used hill of 11.1157 to do this. It might not always matter, but if I do hill of 11.12, if I do the rounded version, then I get a slightly different response. If I round too early, then I can get an incorrect answer. If this was just a little bit, higher, if I used hill of 11.13, if the question was slightly different, and I used the rounded version, I would actually get this wrong. So then we've put in our answers, 8.95, I think it was after rounding. Let's just double check. Yep, 8.95. So the last part of this question just wants us to find the value of the gradient at capital A, correct to 1 decimal place. This is pretty simple. We can use either the gradient for the curved section here on the left, or the gradient for the straight section here on the right. I'm going to use the gradient for the curved section just because I already have a function for that defined in my calculator. So I can just type gradient, my predefined function of 11.1157. Again, we're still using the unrounded version because that's a more accurate way to do things. We get negative 0.0948. So then we go back to our question and we double check. It wants it to correct to 1 decimal place. So if we have negative 0.09 blah blah blah, that just rounds to negative 0.1, and we're done. I think probably the most difficult part of this question is just keeping on track of which functions are your gradient and which functions are your actual hill and which functions are your cable, because we have a lot of different functions in this. If you're not 100% sure about what you're being asked for, like in this part C, in this part B, then you will get the question wrong. Overall, I hope this has been helpful for you. If you have any questions about what we've done, please leave a comment. Good luck with the rest of Math Methods.